The lower the value of the fitness, the better will be the solution. That means for any such violation of the functional constant, so I'll have to add this particular penalty. Now to summarize, for a maximization problem, I'll have to subtract the penalty. For a minimization problem, I'll have to add the penalty. So I hope I'm clear to all of you. And this particular penalty is nothing but a positive quantity. How to determine? For the ith solution, the penalty is denoted by Pi, that is nothing but C is a constant, user defined constant, multiplied by summation k equals to 1 to q phi ik capital X square. Now what is this phi ik capital X? That is nothing but the violation of the functional constant. The kth functional constant, its violation corresponding to your ith GA string. Okay. Now this phi ikx, it could be either positive or it could be negative. And that is why to make it positive, I'm going to consider its square term. Okay. So this will become a positive quantity. You sum them up, after that you multiply by a constant user defined value. C could be 10, it could be 20, it could be 100 depending on the problem, and this is one user defined constant. So ultimately you'll be getting a huge number as penalty, and that particular penalty has to be either added or subtracted depending on the nature of the problem, whether it is maximized problem or minimization problem. Okay, now how to implement? To implement it, actually I'm going to take the help of three concepts. One is called the concept of static penalty. The second one is a concept of dynamic penalty, and the third one is a concept of adaptive penalty. So I'm just going to discuss one after another. Now let me concentrate on the concept of the static penalty. Now supposing that I'm solving one minimization problem. Now the modified fitness of the ith solution, that is nothing but capital Fi capital X is nothing but small fi capital X plus summation k equals to 1 to q ckr. So this I'm going to explain in much more details because this is very important. Then comes your, it is multiplied by phi ikx square. This I've already explained. Okay, why did I put square? That also I have explained. Now what is this CKR? CKR is known as the rth level violation of kth constant. Let me repeat. So CKR is nothing but rth level violation of kth constraint. How to determine? How does a user define those values? So let me explain all such things in details. Okay, let me take a very simple example. Supposing that very practical example, supposing that wherever I am, say, taking this particular lecture class, so at the top of my head, there is a ceiling fan. You cannot see it, there is a ceiling fan running. Okay, and that particular blades of the ceiling fan, that is supported by one shaft, 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 mechanical shaft. Okay, now this is one scenario. The second scenario could be, in place of that ceiling fan, supposing that on my left hand side or my right hand side, there is one table fan, pedestrian sort of thing, table fan sort of thing. And once again, the blades of the table fan, that will be supported by another shaft, shaft, mechanical shaft. Okay. Now, whenever I am delivering the lecture, supposing that there is a failure of the shaft of the ceiling fan, what will happen to me? There will be a fatal accident. Are you getting my point? Because the ceiling fan is going to fall on my head. On the other hand, in the second example, if there is a failure on the shaft of that particular table fan, so the blades of the table fan are going to hit me towards my side, either from the left hand side or my right hand side. There will be an accident, but in second case, the accident may not be so much fatal. So I hope you got the practical example. Okay. Now, which one is more dangerous? The shaft used in the ceiling fan is much more dangerous compared to the shaft used in the table fan. So, if I want to find out the shape design for the shaft used in ceiling fan and the shape design of the shaft used in your table fan, now in which case I'll have to take more care. Definitely, I'll have to take more care on the shaft of the ceiling fan. I'll have to put more factor of safety there. Okay, that means the rth level violation of the kth constraint. So if the problem is a problem of ceiling fan, definitely CKR value has to be more compared to the problem of the shaft related to the table fan. So depending on the utility, the user is going to define what should be the value for this particular CKR. I hope you got the practical importance of selecting so this particular the CKR value. Okay. So depending, supposing that I have got 10 functional constraints, all 10 functional constraints may not be equally dangerous. Okay. Or may not be equally important. So if you find out of 10 a few functional constraints which is very important, whose violation should not be tolerated, definitely you'll have to put more weightage, more CKR value on this particular the functional constraint. I hope you got the idea how to determine so this particular CKR value. And once you've got, you can find out the penalty term, you can find out the modified fitness. Now the GA will run based on the modified fitness, but not on the original fitness, that is small FIX. So GA will run on the fitness information, the modified fitness information that is denoted by capital FIX. Okay, so I hope I am clear to all of you this particular the static penalty. Now I am going to concentrate on the concept of dynamic penalty, which is very important. Now, according to the dynamic penalty, the modified fitness capital FIX is nothing but the original fitness small FIX plus CT raised to the power alpha. I am going to define those terms. Summation k equals to 1 to q mod value of phi ikx raised to the power beta. Now here, so this Q, you know, Q is nothing but the total number of functional constants. What is C? C is the user defined constant, might be 10, 20, 30, 100, depending on the problem. T is nothing but is your T is nothing but the number of generation or number of iteration. Alpha is a constant, might be 2, 3, 4, something like this. And beta is another constant, could be 2, 3, 4, something like this. So these are all user defined constant like C, alpha, beta. These are all user defined constant. For the first iteration or the first generation, T is kept equal to 1. Then T will become 2, 3, 4, and so on. Okay. Now, what is the reason behind going for this penalty, dynamic penalty? Now to go for this dynamic penalty, now if I put t equals to 1, I'll be getting knowing the value for this C, alpha and beta and the violation of the functional constraint. Okay, so I can find out what is the penalty term. So I can find out the modified fitness. But in the first generation, t will be put equals to 1. Second generation, t is equals to 2. Third generation, t is put equal to 3. That means as generation proceeds, the numerical value of the penalty is going to increase. What does it mean? That means initially, I'm not putting much penalty on constant violation. I'm putting less penalty. But as iteration proceeds, if there is any violation of the functional constraint, I'm putting more penalty. What does it mean? That means initially you allow some solution to participate in GSR, and then gradually you put more pressure. If there is a violation, put more penalty. So as iteration proceeds, as if I'm going to put more pressure. Let me take a very simple example, very practical example, which all of you will face in your professional career. Okay, and let me take one example. The way we select our faculty members for any educational institute. You know, the faculty members are generally selected at the level of assistant professor, associate professor, and full professor. And all of you might be knowing, at the level of assistant professor, we select a very large number of faculty members. Okay, but whenever we give promotion to associate or from associate to full professor, we give generally promotion to less number of faculty members, less number of candidates. Although initially we select a large number of faculty as the assistant professor level. Are you getting my point? Same is true here. As if in the early iteration, you put less penalty so that you allow the solutions to participate in GSR. You allow many people to join as assistant professor, but all assistant professor may not become associate, all associate may not become full professor. Are you getting my point? So we put more and more pressure. As we go to the higher level and higher level, we put more and more pressure. Are you getting my point? This is true here. So this is true here in your dynamic penalty. Initially, penalty is less. With the number of iterations, penalty is going to increase. By doing that, I'm going to give more pressure, and consequently, there is a possibility it will help the GA to identify that globally optimal solution easily. So this is the concept of your dynamic penalty. I'll be solving one numerical example. Don't worry. You'll see that it will become 100% clear. Okay. Now I'm going for the concept of adaptive penalty, which is also very important. Now, according to the concept of adaptive penalty, the modified fitness capital FIX is nothing but small FIX plus summation k equals to 1 to q lambda kt phi ikx square. Once again, phi ikx is nothing but the deviation. Okay. Now here there is one parameter that is user defined, and after that with the iteration that will be calculated using this particular relation. Okay. Now this is nothing but lambda kt, lambda t. Okay. Now initially it will be user defined. After that I'm going to calculate using this particular relation. Now remember one thing, for the static penalty and the dynamic penalty, if there is no violation of the functional constraint, the penalty term is put equal to 0. But that is not the case in case of adaptive penalty. In case of adaptive penalty, if there is a violation of functional constraint, we put more amount of penalty. If there is no violation of functional constraint, we put a penalty which is very small. Okay. So in adaptive penalty, even for your feasible solution, we put some penalty, but that is a smaller penalty. But for infeasible solution, we put some larger or the higher penalty. Okay. Now how to find out? So this lambda t plus 1 is nothing but is your 1 by beta 1 multiplied by lambda t. Lambda t initially is user defined for the feasible solution. That means there is no violation of the functional constraint. Now, how to find out for the infeasible solution? So lambda t plus 1 is nothing but beta 2 multiplied by lambda t. Now here, this beta 1 and beta 2 both are constant, and beta 1 is not equal to beta 2, and beta 1, beta 2 are greater than 1. For example, say I can take beta 1 as 2.0, beta 2 as 4.0. So beta 1 is not equals to beta 2, and beta 1, beta 2 individually they are greater than 1. Okay, how to implement? I'm going to solve one numerical example. Okay, now this is the principle of is your adaptive penalty. Okay, let me repeat. For this adaptive penalty, even if there is a violation of even if there is no violation of functional constraint, that means for the feasible solution we put some small amount of penalty. It is not put equal to 0. And for infeasible solution, wherever there is a violation of the functional constraint, we put a large amount of penalty. Okay, now I'm going to discuss with the help of one numerical example. And as I told, it will become 100% clear to all of you. Okay, so I'm just going to consider one numerical example. I'm going to minimize a function of two variables f of x1, x2, that is equals to x1 plus x2 minus 2x1 square minus x2 square plus x1, x2. So this is the objective function. So this is a minimization problem. Subject to the first functional constant, that is x1 plus x2 is less than 9.5. Second functional constant x1 square plus x2 square minus x1 x2 is greater than 15.0. So there are two functional constants. And the variable bounds x1, x2 are lying between 0 and 5. I hope this is clear to all of you. And very purposefully, I have designed this very simple minimization problem, which is a function of two variables. Let us see how to implement the concept of static penalty, the dynamic penalty, and adaptive penalty. Now, our aim is to find out the penalty values using three different approaches like static penalty, dynamic penalty, and adaptive penalty. And to carry out the hand calculation, I'm considering x1 is equals to 2.0 and x2 equals to 3.0, and they are lying within their respective ranges. Now, I'm going to discuss how to determine the numerical value corresponding to this static penalty, that is denoted by this PS. Now here we have got two number of functional constants, that is Q equals to 2. Now the static penalty denoted by PS, as I discussed, is nothing but summation k equals to 1 to q equals to 2 here, ck phi k x square. So this ck is nothing but the user defined value. That means for the first functional constant, I'll have to assign some value to c, and for the second functional constant, I'll have to assign another value depending on the importance, which I have already discussed a few minutes ago. Okay, now let me consider C1 equals to C2 equals to 10. So I'm going to consider that both the functional constants are equally important. Okay, now, uh, now if you see the first functional constant that is not violated. So let me check it. Let us go back to the problem. Okay, so this is the first functional constant x1 plus x2 is less than 9.5. We have taken x1 equals to 2.0 and x2 equals to 3.0. So 2 plus 3 it is 5. 5 is less than 9.5. Okay, so this particular first functional constant is satisfied. So there is no violation. So according to static penalty, so this penalty value will be equal to 0. Now if you concentrate on the second functional constant, x1 square plus x2 square minus x1 x2. Let us concentrate on the left hand side. So x1 square is 4.0, x2 square is 9.0. So 4 plus 9, 13 minus 2 into 3, that is 6. So 13 minus 6 is 7. 7 cannot be more compared to 15. 7 is not greater compared to 15. Okay, so there is a violation of the second functional constant. How to determine the amount of violation? It is very simple. Separately, you calculate the left hand side numerical value and the right hand side numerical value is already there. That is 15.0. So the left hand side is coming to be equal to 7.0. Right hand side is 15.0. So how much is the deviation? Deviation is nothing but left hand side minus the right hand side. That is your 7 minus 15.0. So that is minus 8.0. I'll request you to put up your audio and video. Please put up your audio and video. Please put up your audio and video. Okay. So it is minus 8.0. So what I do is I'll just restart